minutes. Because of some technical problem, we had to create one new link. Now we are trying to connect it with YouTube. Within 3 or 4 minutes, it will be connected. After that, we will start the session. Please wait for 5 more minutes. Thank you.
ഹലോ ഞാൻ സ്റ്റാർട്ട് ചെയ്തു. അല്ല, യൂട്യൂബ് ലിങ്ക് ഞാൻ തരാം. യൂട്യൂബ് ലിങ്ക് ഞാൻ ഇതിൽ ചാറ്റിലിട്ടൊന്നുണ്ട്. പക്ഷെ അത് പോയില്ലേ. ഞാൻ തരാം, നിങ്ങൾക്ക് തരാം. ഞാൻ ചാറ്റിലിട്ട് തരാം. തുടങ്ങി.
Diana, start ചെയ്യട്ടെ. A very good morning to all. I am happy to see that all the dignitaries and invited speakers have joined the virtual gathering. I am very sorry for the 20 minutes lag due to some technical problems. At the very outset, let's invoke God's blessing with a silent prayer. Respected Principal, Dr. Sister Maggie Jose, Adorable Chief Guest, Dr. Sudev Naduvath, HOD, Dr. Pavati KS, my colleagues, faculty and research scholars from other institutions, and my dear students. Mathematics is not about numbers, equations, computations, or algorithms. It's all about understanding. Graph theory is a branch of mathematics which has a profound application in modeling this understanding. Today, we all are ready to go on an excursion through graph theory with a passionate mathematician, Dr. Sudev Naduvath, Associate Professor, Christ, Deemed to be University, Bangalore. He is my teacher, mentor, and friend, and I am blessed to have a handful of research papers co-authored with Sudev sir. I always got wonderstruck to see that mathematics is passion and relaxation for Sudev sir. He has around 200 publications, 3 books, and his book of research is at least 1 research paper per month. Completing his doctorate degree from Bangalore University in set valuations of discrete structures and their applications, he did his MPhil from Madurai Kamaraj University. He had A career of 15 years in Vidya Engineering College, Thrissur, and he replanted his research plant in Christ deemed to be University, Bangalore, 2 years before. He is an editor and referee in many reputed journals and member in famous academic bodies in his research career. Being a research guide in Christ University, his research career is shooting high into its sense of mathematical fame. With a jovial smile, he always reached out our hearts, and I always enjoyed discussing mathematics with him with much fun and laughter. Even after hours of serious research discussions, I used to feel rejuvenated and energized in his magical presence. His profound humility is simplicity, and it is wrapped in colors of warm rapports of friendship. I can't stop praising you, sir. With full of love and gratitude, St. Mary's Fraternity welcomes you to this academic national webinar. Now I welcome Dr. Sister Maggie Jose, Principal, St. Mary's College, Thrissur, to this academic gathering. I also welcome our dear HOD, Dr. Pavadi KS, our colleagues and students for this gathering. Even in a short notice, a lot of research scholars and faculty members from other prestigious institutions have joined here. I extend a cordial welcome to all the participants. I have already told Sudev sir that this national webinar will be on graph theory, that also in a basic level, so that our UG and PG students can get interest and understand mathematics, especially graph theory, to its great extent. Now I invite Dr. Sudev Naduvath to this virtual gathering to start his excursion of graph theory. Sir, please do present your wisdom. Participants, please switch off your, unmute your voice. Somebody is having voice unmuted. Miss Rija, please mute your voice. Miss Rija Kuriakos, please mute your voice. Okay, sir. You can start your presentation.
Okay, am I audible?
Yes, sir.
Am I visible?
Wait, not, sir. You are not visible, sir. Now you are visible.
I think there is some problem in presenting the. Wait a second.
Okay.
Is the presentation visible now?
Yes, sir.
Okay. Thank you, Dr. Sister Smita Rose, for the wonderful introduction. 1 second. Yeah. Is the presentation visible now?
We can see your stop presenting screen. Like.
Oh, 1 second. Now?
It's coming, sir. Yes. Now it's okay.
Okay. So, I understand that many of the participants are undergraduate students. So this presentation is prepared as a basic graph theory exploration. So I plan to make this talk, actually I don't prefer to call it a talk, rather I would say a discussion. So I want to make it a little more activity oriented, and as this title suggests, let us together make it a pleasant excursion through various problems in graph theory. So I expect all the participants to be active, responsive, and make the presentation, make the discussion live. Okay. Right. At present, I cannot see the chat. Is there any provision for that?
Hello, sir. You can select chat option from your
Present
laptop.
It is full screen.
Okay. That you can manage, I think.
1 second, let me check. Is the presentation visible now?
Yes, sir.
Presentation visible?
Yes, sir.
Now?
Now also.
Okay. Now I cannot see the chat.
You have joined through 2 connections. So in one connection, I think you can see the chat, sir.
Let me join through my mobile also.
Yes, sir.
Okay. Yeah. Anyway, we can start the presentation. No, not presentation. We can start the discussion. Okay. So, basically, what is a graph? You can use your chat box to respond. In UG, I think we don't have graph theory in Calicut University, right?
No, sir.
In other colleges, in other universities, I think they may be knowing that. So, we can see that a graph can be considered as an ordered pair, V comma E, where V is a set of vertices, which are also called nodes or points, and another set, capital E, which are called edges, which are the connecting lines between 2 vertices. Okay, so basically a graph can be considered as an ordered pair of 2 sets. The first one is a set of vertices or points, and the second set is a set of lines connecting the vertices. So the commencement of graph theory is from the well-known 7 bridge problem. What is that problem? In the city of Königsberg, we can see 7 bridges across the river Briggen, connecting 2 bank areas and 2 islands, as shown in the model in the slide. So the problem was to find a path or a track which covers every bridge exactly once. So it was a problem. It was the problem caused for the origination of graph theory. So here you can see 2 bank areas. One, here the other bank area. These 2 are islands, and we can see 7 bridges connecting these 2 bank areas of the river and the 2 islands. The problem is we have to find out a path or track which covers every bridge exactly once. So in the first half of the 17th century, Swiss mathematician Leonhard Euler introduced a graphical model. That was the first graphical model in the history of mathematics, I think. Leonhard Euler introduced a graphical model to this problem by representing each land area by a vertex. So there will be 4 vertices, 2 corresponding to 2 bank areas. In this figure, the land areas can be B and C, and 2 islands A and B. And each bridge is represented by an edge. So there is a model in which 4 vertices and 7 edges. And using this graphical model, Euler later found that we cannot find out such a track covering each bridge exactly once. So that was the first problem in graph theory. Right. So the conclusion was such a journey would be possible only if there were no land areas with odd number of bridges leading to them. Okay. So here you can see that when we consider all land areas, there are odd number of bridges leading to each and every land area. That is why we cannot find out a track which covers every bridge exactly once. Okay, so this was the first problem in graph theory, and we can think over a different scenario. If the repetition of bridges is permitted, what is the minimum number of bridges that must be traversed to conduct a road trip that crosses 7 bridges at least once? Can you think over it? Somebody please respond. Sister, is there any message in the chat box? Any response?
Somebody is saying 1, some say 0. Vimalraj says 1. Tyagaraj says 0.
Can you put a track covering all bridges at least once, starting from A? How is it possible? Starting from A to C, C to D, B to B, then back here, then here. So this is a track. Did you notice that? From A to C, C to D, D to B, B to A, then we have to cover this, then back. So one additional traversal is there, back to here again. So what is the minimum possible number of repeat? Here the conclusion is such a journey is possible only if there were no land areas with an odd number of bridges leading to them. So at least how many edges? Anybody answered 2?
No, sir.
So we have to make every edge even, then only it is possible. So we may have to traverse, we may have to repeat at least 2 edges. Okay, so that is an application or a modification of Königsberg's problem. Yeah. Now, what is the relevance of graph theory basically? Here you can see a map of our nation in which the capital cities are connected by road networks. Okay? So it's a graphical representation of the road networks. So, if suppose that a salesman has to travel across cities and has to start from a city and finish at the same city and has to visit each and every city exactly once. It is a routing problem. Is it okay? So routing problems are the first and immediate applications of graph theory. So there are so many ways to find out the routes, and the salesman has to find out the best possible route. The best possible in the sense, how do we find out the best possible route? Any idea how do we find out the best possible route? When we travel, we have to consider so many aspects, right? The distance, sometimes we may have to consider the cost of travel, we have to consider the time taken for the journey, we have to consider so many aspects, so many points we need to consider. And our objective is to optimize many of the constraints. Okay, so if cost of the journey is a parameter, here you can see one edge connecting Trivandrum and Chennai. So there will be a cost associated with that, right? If it is time, we can say that 9 hours or 10 hours. So we can assign that number to that particular edge. So in a similar way, the cost of journey can be assigned to each and every edge as a label or as a weight. So such a graph is known as a weighted graph. Okay. Sometimes we may have to consider time, sometimes we may have to consider cost, sometimes we may have to consider other parameters also. The connectivity we may have to consider, the condition of the road we may have to consider. All these parameters are to be represented by some numerical value. That numerical value is known as the weight associated with the corresponding edge or route. Okay, so out of the possibilities available, the salesman has to find out the best possible one. Okay. So according to different routes or different route map, there are different solutions. So we cannot discuss a general solution for that. But we can discuss the point connectivity here. What do you mean by connectivity? What do you understand by the term connectivity? How can we say that a particular city is reachable from another city? Any idea in real life? Is there anybody responding?
If there is a, Arya Prakash is responding like if there is a path between them, we can connect.
Yeah. What do you mean by a path then? A path is a path we can identify as a route. Okay. So if we want to travel from Trivandrum to Delhi, how can we travel? Trivandrum is here. So there is no direct road, direct edge from here, from Trivandrum to Delhi, right? So we may have to cover intermediate cities and then we have to reach there, isn't it? So a path or a route can be considered as a combination of vertices and edges. Okay? A combination of vertices and edges. Or it can be considered as an alternating sequence of vertices and edges. So how can we say that a city is reachable from another city, or a vertex is reachable from each city can be represented by a vertex? Okay. So how can we say that in a graph a vertex is reachable from other vertex? That means when there exists a path. What is a path? A path is an alternating sequence of vertices and edges. There exists a path between those two vertices. Okay. So consider the network, road network connecting the capital cities of every state in India. Can we say that this network is connected? How do we say that a particular network is connected? What do you mean by the term connected? That means if we consider the graph, every vertex should be reachable from all other vertices. That means every city is reachable from all other capital cities in India. Okay. So if we consider the graph consisting of all capital cities of India, can we say that it is connected? Respond in the chat box, please.
Yes, Arya has said yes. You can unmute and say, okay, participants.
Yeah, if we consider the capital cities of Lakshadweep and Andaman and Nicobar Islands, we cannot find out any road network from other cities to the capital city Kavaratti and the capital city Port Blair. In that aspect, we cannot say that the network is, the graph is connected or the network is connected. But when we consider the mainland area, every capital city is reachable from other capital cities. In that aspect, we can say that road network is connected. Okay. So from the routing problem, we have so many notions, so many concepts in graph theory, like connectedness. Connectedness I have already mentioned. Weighted graph also I have mentioned. And spanning tree. Spanning tree, what do you mean by spanning tree or spanning subgraph? How do we find out a subgraph of a graph? As we know that it is a structure consisting of two sets, isn't it? So whatever be the operations defined for sets can be extended to graphs also. So just like subsets to sets, we can define subgraphs to graphs also. So how do we define subgraphs? In graph, we have two sets, vertex set and edge set. So how do we define subgraph? Here we have to consider the subset condition for vertex set and edge set. Okay, either the vertex set of, how can we say that? Suppose that H is a subgraph of, how can we say that H is a subgraph of the graph G?
If H is a subgraph of a graph G, then the vertex set of H is a subset of the vertex set of G, and the edge set of H is a subset of the edge set of G.
Correct only, correct, very correct. So
Thank you, sir.
Spanning subgraph means the vertex set of H should be
Is
equal
same
to
as the
same as
vertex
the
set of
vertex set of
G.
and edge set is a proper subset of the graph G. Right. So what is a tree? A tree is a connected graph which has
Cyclic.
No cycles.
No closed graphs. That means no cycles.
Cycles.
So a spanning tree is a subgraph of the given graph G with the full vertex set as its vertex set, and the edge set is a subset of the given graph. Okay, and that subgraph will not have cycles also. So finding out spanning trees is an interesting problem in graph theory. And like that, we have shortest path problems also. What is shortest path problems? When we discussed the traveling salesman's problem, we mentioned some points, right? When we assign a route, we have to consider many points like cost, time, many other parameters. All the parameter concerned can be mentioned numerically and can be assigned as a weight to the corresponding edge. So when we consider the weighted graph, we have to find out a shortest weight path from one point to another point, from the source to the destination. Okay, such problems are also very much interesting. So there are several shortest path problems in graph theory. So all these problems are generated from the connectedness and connectivity. Okay. Yeah. Now there is another interesting problem. You can see three houses or three cottages on a plane, and each of these cottages is to be connected to three utilities. We can call the utilities as water, gas, and electricity connected through pipelines. Okay. So the question is it possible to connect these three utilities, water, gas, and electricity, to three cottages without any crossing of pipelines? Is it possible? From the figure itself you can see. So what is this problem? We have to connect three utilities to three houses or three cottages through pipelines. So is it possible to connect these utilities to the cottages without any crossing of pipelines, crossing of conduits? What do you think? There will be 9 connections, right? 3 utilities, 3 cottages. So 3 into 3. Can we make all these 9 connections without any lines crossing each other? So as the it is evident from the figure. It may not be possible. At least one crossing will be there. Isn't it?
Many have responded no, sir.
Yeah. So this problem is also mentioned using graph theory or represented using graph theory. And if we can find out a graph such that its edges do not cross, such a graph is called a planar graph, and this particular problem led to the commencement of a new area of graph theory called topological graph theory or planar graph theory. Okay. So I have a question. If there are 4 cottages and 2 utilities, if there are 4 cottages and 2 utilities, will it be possible to connect the 2 utilities to 4 cottages with any crossover? We have 4 cottages and 2 utilities, say water and electricity. So is it possible to connect these 2 utilities to 4 cottages, all of the 4 cottages, without any lines crossing each other? Please respond.
Yes, sir.
It is possible. So if 5 cottages are there and 2 utilities, is it possible? Please respond.
They are answering no. 3 have answered. Ravati, Tyagarajan have answered no.
5 cottages and 2 utilities. Not possible?
But I think it is possible.
It is possible, yes. When we consider 4 utilities and 3 utilities and 4 cottages, is it possible?
No.
No. So, what makes this impossible? Here we can partition the graph into the vertex set of the graph into 2. One partition represent cottages. So 3 vertices represent cottages and another 3 vertices represent utilities, right? So in 2 partitions, if we have 3 or more vertices, obviously we cannot find out a graph in which there will be a crossover of edges in such graphs. Okay, so that is utility problem. Yeah, now here you see what is the smallest number of people present in a gathering to ensure that 3 of them are mutual friends or 3 of them are mutual strangers. Is the problem clear to you? We have to find out the smallest number of people to attend in a gathering so that either 3 of the participants are mutual friends or 3 of them are mutual strangers. 3 of them are mutual friends or 3 of them are mutual strangers. What is the smallest number? Like that. Any idea?
Naisimul responded as 6.
Reason you have to mention. Okay, here you can see if there are 4 participants. When we take 2 participants, either they will be friends or they will be strangers to each other, isn't it? So we can represent friends by individuals are friends. We can represent a blue edge in between the corresponding vertices. If 2 individuals are strangers, we can represent that relation by red edges between the corresponding vertices. So if we take 4 members in the party or in the gathering, here in the first graph we can see that here we cannot find out 3 vertices which are mutually adjacent. 3 vertices which are mutually adjacent in the sense 3 corresponding individuals are friends. In a similar way, we cannot find out 3 vertices in which 3 vertices which are mutually adjacent by red edges. That means we cannot find out 3 individuals who are mutually strangers. Okay. And again, if we take 5 vertices, we can arrange them in such a way that no 3 of them are mutual friends or no 3 of them are mutual strangers. Obviously, 4 and 5 we cannot take. So the next case is 6. If we have 6 individuals in the gathering, here we can see if we draw edges between them, there will be at least 2 blue edges or at least 2 red edges. So 6 is the smallest number of people required in a gathering to ensure that 3 of them are mutual friends or 3 of them are mutual strangers. So this particular problem is known as 3 strangers or 3 friends problem. Okay. So it is also a problem related to connectivity. Now, just carefully you can read this problem. A job placement director in a college has contacted a number of companies he knows. For what? To conduct a placement drive for 6 trained students. The names of the students are also given. Same material. 6 students are there. And he found 6 companies, each of which is willing to offer a position to a qualified student who is interested in the offer. The 6 job areas are also given, like designing, banking, construction, architecture, marketing and teaching. And the 6 students has to apply for the positions also. So the application status is also given. The first student Ram has applied for the post architecture. He has applied for banking also. He has applied for construction. Okay. The second student Sam has applied for the jobs design, marketing and teaching. Like that 6 students have applied and their application areas are listed here. Okay. So the problem is, how can this situation be represented by a graph? Or how can we represent this situation by a graph, using graphs? And the second question is it possible for a student to get a job of his preference, his or her preference? This particular problem is known as job hunter's problem, and actually this problem is called assignment problem, job assignment problem or job allocation problem in operations research. It can be solved using graphs also. So how do we represent this situation using graphs? Any idea? And is it possible for a student to get a job of his or her preference? How do we solve this problem using graphs? So here you can see a model. 6 students are represented by vertices of one kind and include those vertices in a partition, and the 6 jobs can be represented by another type of vertices, black vertices, or let it be, no problem at all. And those vertices can be included in a second partition or second set. And if a particular student has applied for a particular job, draw an edge in between the corresponding vertices. So Ram has applied for architecture, so we can find out an edge here. Ram has applied for banking, so we can find out an edge here, and Ram has applied for construction also. So if a particular student has applied for a particular job, then add edges between the corresponding vertices. Now, how do we solve this problem using graphs? There are 6 jobs and there are 6 applicants. So each applicant should get a job, a single job of their choice, or not their choice, according to their preference. Isn't it? How do we perform this task? So it is very easy. So here Ram has to be assigned any one of these 3 jobs, isn't it? So randomly we select Ram is assigned to architecture. So this particular job cannot be assigned to any other candidate, even if they have applied for. So there are 3 more applications for this particular job. So we have to remove, we cannot assign this particular job to anybody, so we have to remove these 3 edges from the graph. Okay, isn't it? Right. Now, for the second one, so for the second participant, he has applied for 3 jobs. So randomly we can assign one job for him. So if we assign the second candidate Sam the job teaching, the teaching cannot be assigned to any other candidate. That job cannot be assigned to any other candidate. So the other application or edge we have to remove. Isn't it? Like that, we can verify whether every student gets a job of his or her own preference. Okay. So here we can see a model for that. Here we have assigned to Ram the job architecture. Then Sam, here I have assigned, there are several possibilities. Here I have assigned marketing for Sam. Like that I have assigned one job for each applicant according to their choice. Sometimes this particular graph will be weighted also. Maybe a weighted graph. What is a weighted graph? A weighted graph is a graph in which every edge has some weights. What is a weight? It can be a numerical representation of a parameter concerned with that assignment. So if it is a job allocation parameter, there are several parameters related to that, right? Cost associated with the job allocation. Normally we can consider cost associated with the job allocation. So if it is a weighted graph, we may have to consider the optimal assignment also. What do you mean by the optimal assignment? Optimal assignment in the sense, after assigning the jobs, the total cost should be as minimum as possible. Okay. So we have to ensure, while assigning, we have to ensure that the total cost of assignment should be as minimum as possible. So this is an easier way to solve this assignment problem using graphical models. Okay, so if we increase the number of applicants and number of jobs, we will have different problem scenarios and we can find out different solutions. Now, so this particular job hunters problem was instrumental in the development of a new area of graph theory called matching. So matching is a relatively new area in graph theory, and there are a lot of researches happening in matching. So this particular problem is called a bipartite matching. Why is it called bipartite matching? Bipartite means here we can see two partitions, one corresponding to the applicants, which are in which the applicants are not directly related to each other, and in the second partition we can find out jobs. Jobs are also not directly adjacent to or related to each other. If there is a connection, it is from the first partition to the second partition. Such a graph is known as bipartite graph. Okay. So this particular problem is modeled using bipartite graphs, and this particular problem was instrumental in the development of a new area called matching. So what is a matching? Matching can be considered as a collection of edges of the graph in which no two edges incident on the same vertex, in which there exists no two edges incident on the same vertex. Here we can see, in this problem, if we assign the job architecture to run, this edge will be there in the set, then we cannot consider the remaining three edges incident on this particular vertex. Am I correct? Isn't it? So these three edges should not be included in the matching. In a similar way, if Ram is assigned to this particular job, he cannot be assigned with any other jobs also. So these two edges cannot also be considered. So we have to include this particular edge to the matching. In a similar way, we can consider the other candidates. So the collection of these particular edges will form a matching of the given graph G. Clear? So what is a matching? Matching is a collection of edges in which there exists no two edges incident on the same vertex. And this particular problem is called problem of bipartite matching. Yeah.
Hello.
So here we can see another problem. I think all of you know how to play chess. Am I correct?
Yes, sir.
Yeah. So here is a problem. Following the rules of chess, is it possible for a knight to tour on an 8x8 chessboard, visiting each square exactly once and return back to the starting square? So the knight has to start from a particular square, and its move is an L-shaped move. So it can start its journey. And is it possible to travel and cover each and every square exactly once and come back to the starting square? Is it possible? So what do you think?
Vimal say no.
Are you mentioning it from the example I have shown in the slide? it is not a solution. So this 8 by 8 chessboard, each square of the chessboard can be considered as a vertex of a graph, isn't it? Each square can be considered as a vertex of the graph. So if a knight can travel from a particular vertex to another vertex, we can draw an edge in between them. Okay, I want to just model the graph here. This is not a solution at all. So at present, what is it actually? At present, the knight is located at the square number 20. So you can travel from this particular square to either 59, isn't it? Or 20, yeah, it will be. Or this square number 17, or you can travel to this square number 25. So many possibilities are there. If it travels from this particular square to 59, we can draw an edge between this particular square, this particular vertex or the corresponding vertex to the corresponding vertex of this square. Okay. So what do you think? Is it possible to cover all the squares exactly once and come back to the starting square? Is it possible? It's a time consuming problem, and the answer is yes. We can find out a particular track for this knight to travel through each and every square and come back to the starting vertex. Okay, so the number of moves. So the problem is related with the number of moves. So how many moves are required to cover all the squares? So it's an interesting problem, and there are several research papers on the related problems. Okay. So the answer is yes. The answer is yes. And you can find out so many solutions are there. You can find out so many solutions. I just wanted to model the graph here. How to draw the graph. I want to just mention how to draw the graph here. Anyway, this is not a solution. Here, the knight has not covered so many vertices. This particular square, it did not cover. This particular vertex, it did not cover. Okay, so this is not a solution, it's just a model. The solution is, yes, it is possible. So this particular problem is known as knight's tour problem, and we can find out, we can use other chessboards also, chessboards of other shape. 8 by 8 is the standard chessboard which we use to play. We can consider the chessboards of other dimensions also. Instead of 8 by 8, we can take 4 by 4, we can take 6 by 6, we can take 4 by 6, or even different shapes. And we can check whether the knight can traverse each and every square in the corresponding chessboard without any repetition of squares. Okay. So all those problems are very much interesting. You can opt different types of chessboards or different types of boards, and you can study the problem, and you can study the problem for your project also. Right. Yeah. In an 8 by 8 chessboard, the standard chessboard, with such a visiting, such a tour is possible. Now, again we have a chessboard problem. So again we are considering a standard 8 by 8 chessboard, And a queen, I think all of you know the movement of a queen, right? A queen can move vertically and horizontally straight, and it can move diagonally also, through the diagonals of squares also, isn't it? The queen can move straight and it can move diagonally also. So we can say that a queen on the chessboard dominates or attacks the squares it can move to. So if we put a queen here on c2, it can attack vertically straight, it can attack horizontally also, it can attack through the diagonal also, like this, isn't it? So if we have more than one queen, what is the minimum number of queens that can be placed on a chessboard, standard 8x8 chessboard, in such a way that all squares in the chessboard are either occupied or dominated by at least one queen without attacking each other? That is also important. So what is the question? What is the minimum number of queens that can be placed, subject to the condition that we can take any number of queens? So what is the minimum number of queens that can be placed on a chessboard in such a way that all squares in the chessboard are either occupied by a queen or dominated by a queen without attacking each other? Yeah. I want a response from you. Is anybody responding?
No, sir.
You may take a couple of minutes.
Participants, you please unmute and respond.
Any response in the chat box?
No, sir.
So I again repeat this problem. We can take any number of queens according to our requirements. We can put any number of queens on the chessboard. So the problem is about the minimum number of queens that can be placed on the chessboard, standard 8x8 chessboard, in such a way that all squares on the chessboard are either occupied by a queen or dominated by a queen without attacking each other. So if we put a queen on all squares of the bottom line, in the first, the column in the row corresponding to number 1, obviously it dominates all, right? But
Jaya Krishna answered 8.
8 means, that is what I mentioned. If we put here, obviously they will attack each other, isn't it? So 8 is not an answer. And 8 is not required also. Maximum is 8 only. More than 8 we need not take. So here the problem is about the minimum number. If nobody is answering, I can show the example here. What is the number here? It is only one position. We can have different positions also. the minimum number of queens required is 5. Here you can see. All the squares are either occupied by a queen or dominated by a queen. So the answer is 5. Because of this particular problem is also known as 5 queens problem. The importance of this particular problem is because of this problem only the branch of graph theory called domination originated. So this particular 5 queens problem is instrumental in the commencement of introduction of a highly promising research area called domination in graphs. Okay. And another interesting problem is called map coloring problem. So suppose that we have a map of say we can say map of countries or map of states or map of regions, whatever it is. Suppose that we have a map of a region, let us say, or map of a country, whatever it is. How many colors are required to color different regions or provinces or states of that map in such a way that, here we have to consider, in such a way that no two regions sharing the common boundary take the same color. What is the problem? Here we have to color the regions. In such a way that no two regions sharing the common boundary can take the same color. So what is the minimum number of colors required for this purpose? What is the minimum number of colors required for this purpose? Please respond. I think it is a very famous problem. Is there any response in the chat box?
Malavika is responding 3.
3. Any other answer?
Many are 4. Arya, Ginny, Vimalraj, Sunil responded 5. Others responded 4.
Here you can see how many colors are there. How many colors are used here? Just you can check. Four, right? So any map can be colored using any map in a plane can be colored using 4 colors in such a way that no two regions sharing a common boundary have the same color. And this particular theorem is known as 4-color theorem, and it remained as a conjecture for many decades, not even decades, centuries. Okay. So the minimum number of colors required to color a map is 4. Okay. Right. So this is a coloring of regions, right? In a graph, we are coloring the regions. So that is why it is known as map coloring, or it is also known as the face coloring or region coloring. Okay. In a similar way, we can color the vertices also as shown in the picture. So corresponding to every graph, we can find out the number of colors or the colors required for coloring the vertices of the given graph with respect to some conditions. So that type of problem is known as vertex coloring problems. So what is a vertex coloring? Vertex coloring of a graph is an assignment of colors. Colors means it can be labels or weights also. It's a general terminology. Okay, colors can be either colors. Colors in the graph coloring can be assignment of colors, no problem. Assignment of some labels, numbers, or even it can be weights also to the vertices of that graph. Okay. So a proper coloring of a graph is a vertex coloring such that no two vertices sharing a common vertex can have the same color. Okay. So tell me whether it is a proper coloring or not. I have colored the vertices here. Tell me whether it is a proper coloring. Is it a proper coloring? What is a proper coloring? Should be a coloring in which the vertices have in common the oh, there's a mistake.
Adjacent
There's
vertices.
no, yeah, adjacent. Now two vertices adjacent to each other can have a same color. So here you can see two vertices connected by an edge has the same color. So it is not a proper coloring. So how many colors are required for coloring this graph, the vertices of this graph in a proper manner? How many colors are required? What is a proper coloring? Proper coloring is a vertex coloring in which no two adjacent vertices have the same color. There is an error here. As actually it is written for proper edge coloring. Okay. No two vertices joined by an edge should have the same color. So for this particular graph, how many colors are required? How many minimal number of colors are required? How many colors are required? Please respond in the chat box.
Nasimol responded 3, minimum 3.
Minimum
Malavika responded 2.
2. How can we color this particular graph with the two colors? If we take blue and red, consider this particular part. Here, what color can we assign? Either blue or red. So if we assign blue, these two vertices with the same color, isn't it? These two vertices are adjacent but with the same color. If we assign red, again these two vertices, adjacent vertices, will have the same color. So we cannot assign two colors in a proper manner to the vertices of this graph. So at least 3 colors are required. Okay. So corresponding to every graph, this is a problem to find out the minimum number of colors required to color the vertices of the corresponding graph in a proper manner. The minimum number of colors in a proper color, minimal proper color. Right. So that particular number is known as, that minimum number is known as the chromatic number of that particular graph. Right. So in a similar way, we can define the notion of edge coloring also. So how do we define the edge coloring? How do we define the edge coloring? Edge coloring in which we assign colors to the edges of the graph in such a way that no two edges sharing a common vertex can have the same color. What is it? We assign colors to the edges in such a way that no two edges sharing a common vertex can have the same color. So that particular problem is known as edge coloring problem. Okay. So we can discuss an application of this vertex coloring problem. So you can see a timetabling problem. What is it? The mathematics department of a certain college plans to schedule the classes of, how many subjects are there? Graph theory, statistics, linear algebra, advanced calculus, geometry, and modern algebra. 6 subjects. There are 10 students in the class, and they have indicated they have opted the courses for that particular semester. So 10 students are opted for how many subjects? 6 subjects. The first student opted linear algebra and statistics. The second student opted modern algebra, linear algebra, and geometry. And like that, all 10 students opted some courses according to their preference. So how do we schedule the classes in such a way that the class, if one particular student opted 2 subjects, the classes of those 2 subjects cannot be conducted simultaneously. If a particular student opted 2 subjects, the classes for those subjects cannot be conducted simultaneously. So here linear algebra and statistics are opted by the first student. So linear algebra and statistics cannot be conducted at the same time, in the same period. Okay. So how can we use the graph theoretical concepts to solve this timetabling problem? Any idea? The concept of vertex coloring problem, vertex coloring can be extended to this problem. How? Here you can see. Construct the graph whose vertices are 6 subjects. So we have to construct a graph with the 6 subjects, and 2 vertices are made adjacent, or 2 vertices are to be joined by an edge if some student opted those 2 subjects. Okay, so the vertices corresponding to linear algebra and statistics should be joined by an edge because this particular student has opted these 2 subjects. In a similar way, modern algebra, the vertices corresponding to modern algebra, linear algebra, and geometry should be made mutually adjacent, isn't it? Because this particular student opted these 3. Like that, 2 vertices should be joined by an edge if those 2 subjects are opted by some students. Okay, so corresponding to this choice, we can make a graphical model like this. Is it okay? Now, what is the relevance of an edge? There exists an edge between 2 vertices when the corresponding subjects are opted by one student. Okay. So if there exists an edge between 2 vertices, obviously we cannot assign the same period to those subjects. Okay. So the numbers I mentioned in brackets represent the allocation of the period. 1 stands for first period, 2 stands for second period, like that. So if we assign the first period for graph theory, we cannot assign second period for graph theory. Why? Because both graph theory and statistics are opted by a single student. A single student is common in the classes of graph theory and statistics. So we cannot assign 1 here. So we have to assign 2. So this assignment is also considered as a coloring. So color 1 here, color 2 here, like that. Okay. Now, again, statistics and advanced calculus cannot be assigned the same duration because Statistics and advanced calculus have been opted by one student. But here we can see graph theory and advanced calculus are not opted together by any student. So we can assign the same period to this subject because there is no common student. So here we can assign one again. Like that, just like assigning colors, we can assign period using the conditions of vertex coloring. Okay, so this is an application. This particular timetabling problem can be addressed using the concepts of vertex coloring of graphs or graph coloring. Okay, now another question you can see. If a king had 4 sons and wanted to divide his kingdom into 4 regions so that each region had a common boundary with the other 3, could this be done? Is it possible? I have given the solution also. So it is related to the topological graph theory or planar graph theory. So you can see a king had 4 sons and wanted to divide his kingdom into 4 regions so that each region had a common boundary with the other 3. So each region should share the boundaries with the other 3. So here you can see one such division like this. Okay. Actually, I have put a pause there, but it is not working right now. Yes. Here you can see 10 college students, another problem. 10 college students are attending a party and each student has at least one friend present. When a participant A asks each of the other 9 how many friends of theirs are at the party. So one particular participant asks every other participant of the party, what is the question? How many students, how many friends of theirs are at the party? Each student gives a different answer. Each student gives a different answer. So how many friends of capital A are at the party? Is the problem clear? So if all other 9 participants say different numbers, obviously it should start from 1 to, isn't it? 1 to 9. That is one option. So how can we represent this particular problem using graphs? And using graphs, how can we find out the number of friends of capital A? What is the possibility? Here you can see a model. We can check whether it is correct or not. So A is the first person who is asking the other students, right? So when A asks B, B replies that there are 9 friends. My 9 friends are there at the party. So the number associated with B should be 9. If there are 9 friends, we can draw the edge between those vertices, the vertices corresponding to his friends, to represent the relation between the friendship between them. So if there are 9 friends, how many members are there in the party? Only 10. Anyway, he cannot be a friend of himself. So all other 9 participants are the friends of B. So we can draw edges to all other 9 vertices to all other 9 vertices from capital B, because there are 9 fronts for capital B. Isn't it? In a similar way, when A asks C, C replies that there are 8 friends of mine are there at the party. So we can draw 8 edges. So here one vertex will be with the one friend, isn't it? And his friend is B. So we cannot draw any edge from C to this particular vertex because he has only one friend and that friend is B. And C cannot be a friend of C itself. So from C, we have to draw edges to all other vertices, all vertices other than C and this particular vertex, the vertex corresponding to the student who has only one friend, isn't it? Isn't it? So C should also be a friend of A. In a similar way, proceeding like this, we can see that up to F, all participants should be the friends of capital A. And after that, oh, I have made a mistake in the labeling, I think. After that, the students or the participants corresponding to these vertices will not be friends of capital A. And we can see that the number of friends of capital A in the party is 5. In a similar way, we can extend graphical models, we can construct graphical models corresponding to every gathering with respect to the friendship or with respect to the friendship between participants. Okay. Now, here I have not included any solution. So it is for your thought. There are 4 coins, 3 of which are authentic and 1 is fake. How can we say that 1 coin is fake? The fake coin does not weigh the same as an authentic coin. So the fake coins will have less weight. It may weigh slightly less or slightly more. We can take slightly less or whatever, no problem at all. So what is the minimum number of weighings needed to determine which coin is fake, and how can we find out the fake coin? So we can name the 4 coins as 1, 2, 3, 4. Out of these 4 coins, 1 coin is fake. And it may have less weight or more weight. For the time being, we can consider it as less weight. So the fake coin has less weight when compared to the weights of other coins. So how many weighings are required to determine which coin is fake, and how is this process possible? Just you may respond in the chat box. After that, we can wind up. How is it possible? How many weighings are required? So we have a weighing machine, and we have 4 coins also. Using that weighing machine, how can we find out the fake coin? Right.
Vimalraj responded 3.
3. How? If we have a lever type washing machine, weighing machine, then at a time we can compare the weights of two coins, right? So first you compare the coins, say 1 and 2. So that is one case. If they are of the same weight, we can move that and we can weigh 3 and 4, isn't it? So we can construct a decision tree type graph there. So one thing we can do, combine 1 and 2 together and combine 3 and 4 together, first weigh. So if the combination of 1 and 2 weighs less, then 3 and 4 we can take out, isn't it? So that is the first stage. If the combination of 1 and 2 has the less weight, now 3 and 4 cannot be fake coins. So 3 and 4 we can remove. And in the second stage, we can weigh 1 in the first lever and the second coin on the second lever. Then we can weigh. So how many weighings are required there? Only 2, isn't it? Okay. So I have to suggest, I can suggest some interesting reference material for graph theory, interesting books. Some are common. Here you can see one book titled The Fascinating World of Graph Theory. As the name suggests, that book is a very fantastic book and it covers a lot of real life problems and connect those problems to graph theory, and the graph theoretical solutions are described in that book. It's a must read for every young graduate, postgraduate and research students. As the name suggests, it's a fascinating book on graph theory, and it elaborates so many real life practical applications in terms of graph theoretical models and solutions in terms of graph theoretical models. And some others are basic reading on graph theory. Gary Chartrand and Ping Zhang all these are basic models, basic readings. Yeah. So these are my basic references. The reference one is a must read for all graph theory aspirants. The PDF is available online. You can download and read. You can read, and please read that book with utmost care and passion. You will get so many insights to the practical applications of graph theory. Okay. And if you have any questions, I tried my level best to discuss the graph theoretical problems in terms of real life practical problems. I don't know whether it is digested to you, but if you have any questions or queries, you can ask now.
Participants, please unmute and ask if there are any queries. Sir, nobody's having any queries.
Okay. And thank you so much for patient listening. And at any time you can contact me for any type of graph theory related questions and related things. Thank you so much.
Thank you, sir. It was a very wonderful session, and it was like you are telling some graph theoretic stories to us. Now I invite our research scholar Sinu Vijayan for official vote of thanks.
That was a really wonderful session. Thank you, Dr. Sudev sir, for sharing such valuable information with us. As you said, it is an excursion. Since you never bored us with complicated theorems and results. And we are very lucky to have you as a resource person. And most importantly, you gave us an opportunity to interact with you. And thank you, sir. Now, thank you the whole team of. Thank you, sir. Now, thank you the whole team of St. Mary's College, Dr. Sister Maggie Jose, our principal, and Dr. Parvati K.S., our HOD, Dr. Sister Smita Rose, the coordinator of the event, and all the staff and students of the department for initiating such an informative class for us. And the most important part of this webinar is the active participants like you. Thank you all of you for actively participating in this class. Once again, thank you all.
Thank you, Sinu, for your vote of thanks. So once again, from my part, I thank Sudev sir for this wonderful session and for the kind information of the participants. We have written or given the feedback form in the chat box of both YouTube and Google Meet. You can fill the feedback form. It will be activated only today up to 4 p.m. After that, you cannot fill that. And those who have filled the feedback form, we will be providing a certificate to that registered email ID within 1 week. If there are any queries or any doubt about the certificates or anything else, you can contact me. I am putting my phone number in the chat box. I am Sister Smita, coordinator. So please take time to contact me if there are any problem regarding certificates. If you have not filled the feedback form, you will not be provided with a certificate. So thank you. Let's sign off from this session. Thank you, sir. And thank you for all the participants.
Thank you all, and especially thanks for the organizers.